for those who can't make it. All right, so yeah. We're going to look at a few things, and these are the last subtopics that we're going to have covered under differentiation, right? So we're going to, this afternoon, we're going to try to cover parametric equations, right? So we're going to differentiate those, and we look briefly at implicit equations. All right, they're functions, right? You call them functions loosely. And then we'll look at partial fractions. Right? So we look at these three. And that will kind of close us off on differentiation, right? Put us in good stead for test number 2. Right, test number 2. So let's start with that parametric differentiation. Right, I mean, yeah, right. And basically what this is saying, we are used to a function being defined this way. So you have y is a function of x, right? Isn't that what we're used to? Right? So you have, y equal x squared plus 1, that sort of thing. X squared plus x plus 1, that sort of thing we're used to, right? But you will find that at other times, it is better to describe a function um, where the x coordinate is defined in terms of another variable, which we'll call a parameter, right? And then you have y also being described in terms of the parameter t, right? For those of the couple of teachers in the class, you are already introduced in your other courses where x is described in terms of a function of theta, y equal to a function of theta, right? You're familiar with this already, right? And at other times, you can have this situation, right? And it can be the other parameter can be anything, right? So we have t here, that could be time down here. It could be an angle, just to name a few examples, right? And there are times again when these here, these functions can very well be representing, it can be a straight line, right? The relationship can be a straight line, as well as it can be a curve, and then calculus comes into play. What's the gradient there? What's the gradient there, right? So we have to know how to differentiate these parametric functions, right? So let's talk about how we can differentiate them, right? Um, if we were to remember the chain rule, if we apply the chain rule, right? You can actually, use the chain rule. You want to find dy dx. That would be equal to dy dt times dt dx, right? You see that, the chain? It's as though this cancels with that and you're left with dy dx, right? So if you have y as a function of t, right? And you have x as a function of t. Sorry, let me use gt, right? Function gt, right? Well, you'll get dy dt from this. right? You just have to differentiate it. But then notice here you want dt dx, not dx dt. So what you do, you find dx dt, and simply, when you finish, flip it over, right? dt dx is simply 1 over dx dt, right? And that is why sometimes some textbooks would write this here like that. They'd have dy dx is equals to dy dt over dx dt, right? You'll see them writing this. And it's the same thing if you know your little bit of fractions and so, right? And of course, your condition is that this can't be zero, right? If that is zero, well then um, the derivative will not be uh, defined, right? And then you can even do the second derivative. Am I moving too fast there? Did I move it too fast? Anybody's making notes? All right. What are you saying? And then you might be called upon to find the second derivative, right? So if you're finding the second derivative, here's the formula. Second derivative is equals to d dx of the first derivative, right? Which basically is this d dt, right? Because very often you find that dy dx might be in terms of t, right? D dt of dy dx, all divided by dx dt. And this here will ensure that this dt, right? And that dt cancels out, right? Again, if you know your little bit of um, your bit of fractions, right? And you'll end up with d dx of dy dx, which is differentiating the derivative, right? The derivative dy dx, you're differentiating it a second time. That's what it means. Good. So let's take an example or two quickly. Let's take an example or two. So let's say you're given a function, maybe okay, it's x equal t squared, and you got y equal t cubed minus 3t, right? Let's say you have a pair of parametric equations, right? This is minus here. And you want to find, let's say dy dx. You just want to find dy dx, right? Well, you would need, for you to find this, you would need, of course, we said dy dt. You would need dy dt. And from this here, you will get what? 3t squared minus 3. And you also need dx dt, which is 2t, right? And you divide this by this, right? So you end up with, all right, dy dx then, we just said it's going to be dy dt over dx dt, right? Um, oh, yeah, right, which is what? 3t squared, oh my, 3t square. Oh gosh. I knew somebody did make this man better disturb me. No. Yeah. 3t squared minus 3 over, what's that, 2t? I know you probably, if you want to do a bit of simplification, you probably want to put 3 and t squared minus 1 over 2t, you know, that sort of thing. Right? Simple as that. All right. Let's take another example. I mean, for those who are watching the video, you'll just have to slow it down or pause it or whatever they do, right? And you can have little bits of application and so inside, you know. Let's take this one. Let's say you want maybe, okay, Find the equation of the tangent to the curve x equal 2 cos theta, y equal 3 sine theta, right? So you see the x and y being described in terms of theta here, where, all right, they want a tangent, equation with tangent at a particular value of theta. Let's call it, um, I'm not sure if you know what this is. This is an angle in radians, right? When you're doing calculus, the angle has to be measured in radians, right? Not degrees, because the whole idea in calculus is that the angles of the numerical value has to be very small. Remember, the whole idea of calculus is small increment, right? We're dealing with values that are small, right? So pi upon 4, I think, is what, 45 degrees, right? 45 is a big number numerically, right? But pi over 4, 3.14 divided by 4 is a very small number, right? And it suits the definitions of calculus, right? Small increment, small values, right? Good. So from this, what do we have? dx, all right. Let me go dy, d theta will be what? 3, what's that? 3 cos theta. And dx d theta is equal to minus 2 sine theta, right? So dy dx is going to be what? 3 cos theta over minus 2 sine theta, right? For the guys, I'm just writing this, right? For those who know a little bit of this, this is what um, yeah, cos over sine is what they call cot, right? Or cotangent theta. Well, the teachers who they do that extra course, couple of courses now they're doing in analytic and geometry and trigonometry. They would know all of that. But if you don't know what this is, don't worry, you can stick with this, right? You can stick with that. Good. So that's the value for dy dx. So the gradient of this curve, when gradient when theta is pi over 4, right? You just substitute inside here, right? So you get um, minus 1.5. Well, if you don't know what this is, you could just do this. You could just do this. 3 cos of pi over 4 over minus 2 sine of pi over 4, right? And if you don't know what this is, and so you don't know how to use it in the calculator, simply change this to what, 45 degrees, is it? Pi over 2 is 90, yes. Pi over 4 is 45, right? You put that in the calculator, and you should get, when you finish, minus 1.5, right? You should get minus 1.5. So that's your gradient there. And your next move now, your next move is to find the, well, you got to find, remember, for you to get the equation of the tangent, you got to get a point on this curve, right? And that point you can find from substituting theta equal pi over 4 in this equation here, right? So x then is going to be equal to, all right, you want a point, right? Remember, you want a point on curve. So x is going to be 2 cos of pi over 4. Y is going to be 3 sine of pi over 4. And these values are going to turn out to be root 2. This one is going to be 3 root 2 over 2, right? So you have now some values, right? So you have an x and y coordinate. You put that in, you do that thing where you call it, um, what is it? Point slope form of the equation. Is that it? 3 root 2 over 2 equal minus 1.5 x minus root 2, right? If you want to try to simplify that, be my guest, right? You can leave it like that, or you can do some simplification, yes. You'll just have a lot of horrible decimals what would this be? Minus 1.5 is that 3 over 2. You may or may not be able to simplify this and make it look nicer, right? Yeah, but that's your equation basically. That's your tangent equation there, right? Maybe let's do one with the second derivative now, right? Let's see, you want with the second derivative. So let's say you have a parametric equation. X is equals to, say, e to the t power. Y is equals to t squared. Let's say that, right? And they want you to find d squared y over dx squared, right? This I mean the second derivative. Good. So you have to find first derivative first of all. So um, dy dt will be 2t, and the x dt is going to be, well, the same thing, right? Um, the Yes, when you differentiate that, you're going to be left with the same thing, right? Good. So dy dx then, dy dx is going to be this divided by that, right? Which is, we're going to have what? 2t over e to the t, right? That's your answer there. Good. So now um, you have to differentiate a second time, right? So if you remember the formula, I'm going to go back and write the formula one more time. That d square y dx square is equals to d dx of dy dx, which is the same as d dx of dy dx all over dx dt, right? And the reason why you have to do this, we have no way of differentiating dy dx with respect to x. I don't know if you see that. Because dy dx is something with respect to t. It has t inside. If you are able to eliminate t and write dy dx in terms of x, well, then that would be good. You can just differentiate like normal, right? But because we have something with t, this formula, we just can't do this directly, right? And that poses a problem. And therefore, some smart Alec figure out that, oh, what about if we differentiate this here with respect to x, and then when we finish, right? Sorry, I mean this is a d with respect to with respect to t. But we can't differentiate with respect to x because there's no x inside. There's only t here. So we differentiate dy dx with respect to t, and then you divide by dx dt. And we got this already. We got that already, right? So d dt of dy dx is really equal to d dt of, what's it? This here, right? Of 2t over e to the t, right? And when we use the, this is like what we could use the, what do you call it? we could use either the product rule or the quotient rule, right? We can actually do that because this is what we could do here. We can write this as, and I think the product rule is better because this is like 2t e to the minus t. You watch it good, right? So it's equal to d, let me put t dt of 2t e to the minus t, right? Which is equals to, you remember that thing? 2t times the derivative of this, which is minus e to the minus t plus this here, e to the minus t dot the derivative of 2t is 2, right? So when you simplify all of this now, what do we get here? We have what? Let's put this in front now. Okay, so we got e to the 2e to the minus t. Put this at the back, minus 2t e to the minus t, right? And you can take out what? 2e to the minus t, right? 2e to the minus t bracket. That'll be 1 minus t here, right? Good. So now we have d dt of dy dx. We just have to divide it now. So d square y dx square would be this thing here, 2e to the minus t bracket 1 minus t, all divided by e to the t, right? And if you know a little bit of algebra, you can bring this up here and you end up with 2e to the minus 2t bracket 1 minus t, right? Better know your algebra because I can very well tell you to do a second derivative and you're looking for this all over. And you end up, this is the answer staring you in the face. Right? So, yeah,
Excuse me, sir.
yeah.
One question.
Uh-huh.
In the previous question, you said you used the point slope formula, right?
Oh, all right. You're going back to the last one. All right. Yeah, all right.
Yeah.
Yeah.
Sorry, I waited to see if you would use it back in this question. If maybe I missed something. Um,
No, in this
we
question,
used
we're
a
not,
different.
we're just finding the second derivative. We're not finding no equation of no line and
Uh,
so. This one, you're finding the equation of a line. That's what we end up with here. But in this one, we're
oh,
simply finding the second derivative.
okay. I was gonna ask because when we worked at questions for tutorial, we used a different form, I guess, of the point slope formula than the one you used. So that's what I was gonna ask about.
You use a different one. You know this formula, man, where you put
Yeah,
y minus some value, some y value
well, the
that.
one we used was
Uh,
the one we used was y minus y1 equals m open bracket x minus x1. That's the one
yeah,
we used. So I
that's
wonder
not
if
it.
this is like
Watch
a
this.
different
Watch it.
form.
This here is this
Mm.
value here. It's a value. It's a value for y. This is a value for y. Look here, right? This here I put in that place. And this
Oh,
is
I see
the
it. Okay,
m,
I
right?
see it.
X minus. Yeah. All right, no problem. No problem. It's good
Okay.
that you
Yeah.
were, at least somebody is paying attention to something. Yeah, great. Yeah, the girl is interested in her calculus, right? Um, yeah. All right, good. Good. So I think we covered a bit there on what we did there. Parametric, parametric differentiation, right? So what we're going to look at now, I want to look at a little bit of implicit. I think I have an old. Give me 1 second. Let me just pause the recording. I have an old. Yeah. So let me know if you can see this here, right? So we're looking at what we call implicit functions. Implicit functions. What do we mean by that? What do we mean by that? And we'll talk about what it is, see some examples and so, and then we'll talk about how we can differentiate them and do some other stuff with them. So here we have, all right, a couple of examples. And again, I didn't go heavy into this. I'm just scratching the surface because apart from the teachers in the class who are doing a number of other trigonometry courses and analytic geometry courses, um, not much of it will appeal to the biology student who um, they're not doing so much of the trigonometry and analytic geometry and so on, right? I was funny that the other day. Um, so it was in the first year, the second year students were doing a test. I think it was the first year, is not y'all? And they're doing a test in genetics, and I was asking them if they know what was it I was asking? What is guanine and cytosine, and they looked at me so puzzled, like they don't know what what I'm talking about. Is this the class?
Yes, sir.
Yeah, yeah. Is that what you do in genetics?
Yes, sir. That is partially what our test was based on, a part of it.
How people look at me like, and they couldn't name the four, what was it, protein molecules?
The bases, the protein base.
Yeah, people couldn't. People watching me like, what the hell wrong with this guy? Yeah. If you all know where genetics is today and what they're doing, right? It's amazing, right? It's amazing what you're doing. Anyway, yeah. Let me go. We got quite a bit to cover here. Yeah. So these are some examples, right? We have the circle here, the hyperbola, the ellipse, right? And if you were to try to, what do you say, express the equation explicitly, meaning, you got y on one side and x on the other side, the equations look rather ugly with this radical sign, right? Or this square root sign inside. It looks rather ugly. However, if you were to write it like this, the same equation written this way, look here, x squared plus y squared equal 9. It looks, I mean, it still does look complex, but look nicer without the radical sign, right? Here, you don't have y defined explicitly in terms of x, but y seem to be in the mix, right? It's the value of y, right, is implied. It's not very explicit as you see here. You want to know what's the value of y? Tell me the value of x. I put it in here and I, calculate. Here, though, no. Y is even squared by itself, right? So equations of this form, you call them implicit. Um, these are implicit equations where y is implied, right? So here they are, these three, and I guess a lot of you would say, man, these shapes here, the circle, the hyperbola, the ellipse, they aren't functions, but we do call them functions in calculus and in later mathematics. They do call them functions, right? We kind of slacken up the definition of a function, right? We don't want to restrict ourselves too much. Good. So how do we go about you know differentiating something like this? X squared plus y squared equal 9. How do we do that? Good. So these are some examples here, right? And x differentiating is like x squared or anything with x is not a problem. It's the y that you're worried about, right? Good. So when you differentiate y, you know you get dy dx. That is what we've been doing all the time. This is a little bit extra now. If you differentiate y squared, you will get 2y dy dx. And the reason why is that, remember, y is a function of x. So apart from differentiating the outer function, right, um, where you get 2y, you have to differentiate the inner function y, and when you differentiate that, you get dy dx, right? Chain rule. So you get 2y dy dx is the derivative of y squared. And similarly, you can see the trend. d dx of y cube is, you treat y cube as a function you have to differentiate. You get 3y squared, but then when you differentiate the inner function, the y, you multiply by dy dx, right? And I guess you can guess if I ask you um, to differentiate um, y to the 4, what will you say? Anybody? Hmm? If you observe the trend, what's the trend?
2y3 2y3 to the sorry 2y to the power of
No, you
3.
have a 4. Watch this. It said, what, down here? What, down here? I bring the 2 to the front. That's all. And
Yes.
I reduce the power by 1. Look down here. I bring the 3 to the front, reduce the power by 1. That's how I get this. So you bring the 4 to the
4y
front, you get 4y
3.
cubed. And then you always stick in dy dx at the back here. This comes from differentiating whatever function is in the place of y, right? And that's it. So you're going to use this now to differentiate, well, any implicit function, right? All right, don't mind. I have to erase all of this. All right. Good. So look at this one. What's this now? What's this craziness here? Oh, yeah. All right, good. Look at this one. So, yeah, we want to find the gradients of the tangents to this circle. So this is a circle here. And we just want the gradient of this line here and this line here, right? These are the two tangents to the curve at these 2 points, right? When x equal 1. So what do we do? Right? We're looking for two gradients really, not one. So, all right, we simply take the function x squared plus y squared equal 9, and we differentiate. When you differentiate 2x, you get x squared, you get 2x. When you differentiate y squared, you get 2y dy dx. When you differentiate 9, you get 0. And you do some rearrangement, and you get dy dx equal minus x over y. Good. So you want to know what's the gradient when x equal 1, right? So what you need, notice dy dx involves x and y, right? So we got x equal 1, but we need a y value. Good. So what we do now, we put x equal 1 in this equation here, and we solve for y, and we'll get two values. You notice? We'll get two values. And two values are positive 2 root 2, and the other one is minus 2 root 2. So dy dx then becomes 1 over, well, we're dealing with plus or minus 2 root 2. You get two values. These are two values, right? And those are your gradients. One of them is positive, one is negative. Because when you look back, if I'm to go back here, one of the tangent is going up like that, so that would have a positive gradient, and this tangent would have a negative gradient, right? Look back at it good. Differentiate there. Uh, yeah. Make dy dx a subject, you get that. to evaluate this gradient, you need an x value, you need a y value. We were given an x value, but not a y value. But we can calculate the y value because we have an equation connecting x and y here, right? X squared plus y squared equal 9. So if we know x is 1, we can get the two values for y. In this case, you get two values, right? Not one. We get them. When we finish, we put the x value and the y value in the gradient function, that is, minus x over y. And you get the two values here, right? And again, you have to remember your algebra. How does this become that? Don't ask me. All right, maybe let's do another one. So, what are we doing here? Something is wrong there. All right, maybe something is wrong. Let me take this one. I don't know where all these things coming from. I keep deleting them every year, and they turn up back again. All right. They want the gradients of the tangent to the ellipse, right? And this is the ellipse here. And they can go further, right? We can actually not just ask for the gradient, we can ask for the equation of the tangent, right? We can ask for the equation. It's more than one, right? The gradients of the tangents, I think it should be two, right? There should be an S here. But again, oh, excuse me, feeling sleepy now. I didn't sleep this day. Everybody wishing me to sleep soundly and so, right? And not giving them the test. And for that reason, I didn't get any sleep. I got to be very bad-minded people wishing you, they wish you and you get no sleep. Somebody said they want me to sleep heavenly tonight. Like they want me to pass out and go to heaven. Oh gosh. Yeah. So let's differentiate. All right. So we differentiate and this is a smart bit of algebra here. Instead of differentiating with these, fractions, multiply everything by the LCM of 4 and 9, which is 36, and you get this. You get 9x squared plus 4y squared equal 36, right? And now you can differentiate. So you differentiate 9x squared, you get 18x, okay? And down here, 4y squared, when you differentiate it, you get 8y dy dx equal to, well, 36 when you differentiate, you get 0, right? And then you make dy dx a subject, you end up with that. For you to evaluate this here, you need an x value and a y value. We know x is 1, but we don't know what y is. So we have to evaluate y using this, maybe this equation here, right? Right? We put x equal 1 and we evaluate y, and you get that. And you take these two now and put it inside of here. And I think you should end up with plus or minus root 3 over 2. Right? And maybe you can, on your own, if I ask you, find, I can ask you not just to stop at the gradients, right? The gradient at x equal 1, I can ask you, well, find the equation of the tangents, right? And maybe you could jot this down and try it. Find the equation of the tangent. You already got the gradients. You got 2 points, right? You got 2 points. And therefore, you can now calculate the equation of the tangent using your knowledge of what you did in algebra, right? So that's a little bit there on implicit functions, right? Mm, yeah, I'm not going to go further than this because I'm thinking you can find the second derivative here as well if you want. No need for that because it's very simple now. If you get dy dx equal this, you can now find the second derivative, right? Maybe you can write this, treat it as a quotient and then, use the quotient rule to find the second derivative, right? I'll spare you all of that. Good. So y'all want us to take a little break before we go on to the last point, the last subtopic? Or you want us to go through? You tell me. Tell me something quick. You want me to continue or take a break?
We can continue if anybody have no problem.
All right. All right. All right. Somebody wants to finish with calculus and done with it. I myself, I want to go have my dinner and sleep. Yeah. So now we're going to deal with, we want to deal with a situation where you might have to differentiate something, right? And using, let me give you an example. Let me give you an example. So we're dealing with differentiation using partial fractions. Did we do this? I wonder if we do this we do this inside algebra. I'm trying to remember now. So let's say you have to differentiate something like this. You're given, okay, y equal 5x minus 1 over, right? You have to find dy dx, right? You have to find it. Now, when you look at this looks like a quotient, huh? And one might be tempted to say, man, let me use the quotient rule here. But you would see, you'd have a very horrible denominator. You'll have, it'd be very, very complex, right? So instead of doing this, what we could do is take this and we break it up, right? This is what we call a proper um, quotient, right? It's a rational function, but it's a proper rational function in that the power in the numerator is less than, it's not equal to or greater than the one in the denominator. So what we can do with this, we can break this up. We can take this, right? Okay, when we take this at the bottom here, let's see, we can factorize that to be, right? Now this here, y is equals to this. This here can be broken up further into something a over x minus 2 plus something else, we call it b over x plus 1, right? So what we're doing here, we're breaking this up into what we call partial fractions. Partial fractions is that we take this thing and we break it up into two. Because if you were to add these two things, this will be your LCM. X minus 2 times x plus 1 will be your LCM, right? And then some number up here, when you do your mathematics or your arithmetic, your fractions, you'll get back the 5x minus 1 up there, right? So our task then is to find what a and what b is, right? So what we could do is multiply both sides by this denominator here, right? And you end up with 5x minus 1 equal a bracket x plus 1 plus b bracket x minus 2. And our next task now is to evaluate what A is and what B is. And there are numerous ways you can do that, right? There are numerous ways you can find what A and B are, right? So let's see if we can get what A and B are, right? So this is one way. To get rid of this B, we can say let x equal 2, right? Look at what happens. 2 minus 2 is 0, so B gone. So 5 times 2 is 10. 10 minus 1 is 9. So this thing becomes 9. All of this, so if x is 2, this is 2 times 1, 3. Sorry, 2 plus 1 is 3. 3 times a is 3a. And that implies that a equals 3. That's all. Next, we want to find the value of b. So we can probably say let x equal minus 1, right? And what that does, that actually kind of eliminates this a, right? So you put minus 1 in here. 5 times minus 1 is minus 5. Minus 1 give you minus 6 equal to minus 1 minus 2 minus 3. You get minus 3b, which implies that b equal 2, right? So we got a value for a, we got a value for b, right? And again, you can always, go to YouTube and type in partial fraction, right? Partial fractions, and you see people develop a lot of different approaches to evaluating, the A and the B and so. Good. So now that we have A and B, so we found A and B, right? So this thing is equal to A as well, is 3. So it's equal to 3 over x minus 2 plus B is 2, 2 over x plus 1, right? So the derivative of, what's this? Derivative of, what was it, 5x minus 1 over, I can't remember what was at the bottom here. I think x squared, what was at the bottom there? X squared minus x minus 2 is really equal to the derivative of 3 over x minus 2 plus the derivative of 2x over 1, right? 2 over x over 1. And you can see this to be what? You can see this as, write that as 3 bracket x minus 2 d dx of that plus d dx of 2 bracket x plus 1. Oh, to the minus 1, right? To the minus 1. Can you see that using your little bit of algebra? I don't know if you can remember your little algebra. And now we can differentiate. We can watch it and see. Take this minus 1, bring it to the front, so you get minus 3. Never trouble what's in the bracket. Minus 1 from the power plus, bring this to the front, multiply. Okay, so this will change to minus 2 bracket x plus 1 to the minus 2, right? And you end up with, all right, minus 3 over x minus 2 square minus 2 over x plus 1 square. And that's your answer there. Quite a bit of work, eh? Quite a bit of work. Good. So let's do another one. This one will involve what we call repeated factors. So let's say you have, all right, fx equal to, you get a x squared plus 1 over x bracket x minus 1 squared. right? So you have what you call a repeated factor inside of the denominator. So what you will have is this will simplify. This will simplify to be a over x, that's one of the factors there, plus b over x minus 1 plus c over x minus 1 squared. So you don't just have b over x minus 1 squared. You have b over x minus 1, c over x minus 1 squared. So you have a third unknown to solve for there, right? Good. So you multiply throughout by x, you multiply throughout by this, right? And you will end up with x squared plus 1 is equals to a bracket x minus 1 square plus bx times x minus 1 plus cx, right? Or to multiply throughout by this denominator here. Good. And now you can you have to try to figure out the value of A, you have to figure out the value of B, and then you're gonna figure out the value of C, right? One at a time. So let's see if we can. What we could do is, all right, look what, if we let what is, and you're able to develop these tricks, you know, as to how you can evaluate A, B, and C easily. When you look at, you know, the approach people are using, right, and different approaches, like, okay, watch this. If I let x equal 0, look at what happens. This expression goes, that expression goes, right? And you're left with, well, down here is going to be 1 equal, what's this? 0 minus 1 square to give you 1. Look at that. A equal 1. You see that? What's this one now? The neat trick, right? The neat trick to get rid of all of these here. So next you said let x equal, what's this neat trick now? X equal 1. Look at what happens. All of this goes, all of that goes, and you're left with 1 squared plus 1, which is 2, equal c, right? So 2 equals c, or c equal 2, whichever one you want to say, right? And then let's go up a little, and let's see if we can find, how do you find, what do you call it? Well, we got to find b, or we got to find b, right? And you can do a lot of things. There is a method called complete comparing coefficients. But you know, you could do as well. You could actually let x be some number. Let x be, all right, let x be, we got 0, we got 1. All right, let me go with 2. Let me go with 2. Right? And let's see what we need to evaluate. B, right? We got to evaluate B. So let's see what happens. So 2 squared plus 1 is 5 is equals to, where we know A is 1, right? So you don't have to worry about that. We know A is 1 already. So we got 2 minus 1, which is 1. 1 squared is 1, right? So you get 1, all right. B times 2, all right, we go with 2 minus 1 is 1. So B times 2 is 2B, right? Plus, and C is 2, right? C is 2, so 2 times 2 is 4. Are we getting it right? So 5 is equals to 5 plus 2b. And the only way this is going to be true is if b equals 0, right? B is 0. So what we're seeing here, in this case, you might say, man, sorry, Mecca, we go through all of this to find out that this is equals to A is what? A is 1 over x plus what was C? C is 2 over x minus 1 squared. Now the middle term here goes away. Not in every case when you're dealing with repeated factors. It so happened that in this one, that term goes away, but not always, right? So therefore, this expression d dx, oh, we're not dealing with dy dx, we're dealing with f, right? I think it's fx, all right. Let me use that notation. So f prime x will be equal to the derivative of this, right? D dx of 1 over x plus d dx of 2 over x minus 1 square, right? Which is x to the minus 1 d dx of that plus d dx of 2 bracket x minus 1 to the minus 2, right? And when we differentiate that, what do we get? We get, all right, minus x to the minus 2 plus, you bring this 2 to the front, you get, all right, I can change this to a minus sign, huh? Minus 2, don't trouble what's in there, to the minus 3, right? Minus 2, minus 4 here, minus 4. So we get minus 1 over x squared minus 4 over x minus 1 cube, right? And that's our derivative. Or maybe we can take out the minus sign totally and put it outside in our bracket and all of that. Right? But be careful. Not every time this middle term is going to go away. In this one, it happened to. At other times, you find a nice value for b, maybe 1 or 2, and you can get fractions and so too. Right? Have I lost you yet? All right. The last one. The last one. And then everybody says they want to go and sleep. They want to eat and sleep, somebody says. All right. Let's say you have one like this. 2x squared plus x plus 8 over x minus 1 x squared plus 9. Look at this one. So in this case, you have what we call a quadratic factor in the denominator. And the mathematicians who checked this out already before us tells us that whenever we have that, a quadratic factor in the denominator, and especially one that you can't like cancel out with, let's say you factorize up here and it cancels with something. It's possible, right? And you can have x minus 1 canceling with something. I'm not sure that can happen here, but you must check all those things, right? Good. So let's say, all right, this one can't cancel. So this here is equal to a over x minus 1 plus bx plus c over x squared plus 9. So whenever there is a quadratic factor in the denominator, in the numerator here, this is what you have to have, bx plus c, right? Good. So what do we do there now? We have to evaluate A, we have to evaluate B, we have to evaluate C, right? So we multiply throughout by this denominator and we get what? We'll get 2x squared plus x plus 8 equal to A times that. So you get A bracket plus x minus 1, right? X minus 1. Good. So we have to find a way, we have to find ways now of getting A, B, and C, what those values are, right? And let's try this. Okay. Let x equal 1. Now what that does, it kills this, eh? Kills this here. When you let x equal 1, what happens here? You got 2 plus 1 is 3 plus 8. You got 11. 11 equal to, what's here? 1 plus 9 Oh my, some horrible numbers now. We got 10a, which implies that a equal 1. That this can happen, right? 11 over 10, which is 1.1. Yeah, those are possibilities too, right? Good. Another thing we can do now is, all right, we got to find what B and C are. So what do you do now? Well, what you could do is you can try some numbers. They have several ways you can do this. Well, let's try some number. Let's say x is 0. What happens? What happens? So that kills all of these over here, and you get 8 equal to, this is 0, right? X is 0, so this gone, and you get what? 1.1 by 9. 1.1 by 9. Somebody please give me a value. Oh. So what is going to happen there? This B is going to be gone, right? So you have plus C times minus 1. See if that's correct. This gone. X is 0. So this gone with that B. So you're left with C times minus 1. So this tells us that C, this implies that C equal to what? When we do all of this, bring this over here, bring this over here, 8, 9 point. Anybody do the mathematics to me?
9.9, sir.
9.9? No, man. Oh, you mean, okay. 9.9 minus the 8 now, right? And I'll give you 1.9. So C is 1.9.
Yes, sir.
Good. So we got A, we got C, and we need to find what now? B, right? Oh, good. So we got to find B now. And you can again we use 1, we use 0. Let X be maybe 2, right? Let's go with 2, or that would give us some horrible numbers. I'm trying to see if I get, I wonder if minus 1 would be a better number. Let's try minus 1, huh? Let's try minus 1, right? So minus 1 square will give us 1. 1 by 2 is 2. 2 minus this 1 is 1. 1 plus 8 is 9. So we got 9 over there. Okay. What happens over here? Minus 1 square is 1 plus 9 is 10. 10 times, what's A? A is 1.1, right? 1.1 plus, we going over here now. We don't know B, right? So down here is going to be minus B plus 1.9 times X is minus 1, right? And we'll have to do some calculations here. This is what? 9 equals to 11. This becomes what? Plus, all right, no, I have to change that to minus 2 bracket 1.9 minus B, right? Good. And all of this, I hope we get a right value. So So we got what? 9 equal 11 minus 2 by 1.9 is giving me what? Anybody working with me? But you want to go and eat and sleep them by say 2
3.8.
times, okay, minus 3.8 plus 2b, right? So, all right, what's this now? 9 equal, what's that? 11 minus 3.8, 7.2
7.2.
plus 2b, right? So all of this will imply that what? B equal what? So 9 minus 7.2 divided by 2.9, B equals 0.9. So we got A, B, and C there, all right?
Yes.
We got A, B, and C. So let's see if we can. So, good. So this whole thing becomes A is over 1.1 over x minus 1 plus what's B? 0.9x plus what's C? Can't see what C is. 1.9, right? 1.9 over x squared plus 9, right? So the derivative of this, right? The derivative of this whole thing here, this long thing here, right? 2x squared plus x plus 8 over this horrible looking is equals to the derivative of 1.1 over x minus 1 plus the derivative of 0.9x plus 1.9 over x squared plus 9, right? Good. So this is hard work no matter how we turn it or twist it, right? So here, okay, we have to make use of all this space. This becomes what? 1.1 bracket x minus 1 to the minus 1. This becomes, we could leave this instead of changing it to a product, right? We can treat it as a quotient, right? We could treat it as a quotient. We'll get what? Let's see. ddx of that plus ddx of, I'm gonna, oh my, write back the same thing, right? Good. So this, when you differentiate that, you get minus 1.1 minus 2, right? When you differentiate this now, what is it? V times the derivative of up here. So you'll get what? All right, plus, okay, V du dx. So you get x squared plus 9 times the derivative of up there is times 0.9 minus u, which is on top of that of there, 0.9x plus 1.9 times the derivative of the bottom, which is 2x, all over x squared plus 9 square, right? And you know, we try to simplify all of that. You'll get what? This will become 1.1 over x minus 1 square. One thing with textbook writing, you know, when the people who wrote it with the textbook, they have some nice numbers, right? When you try to do anything on your own, you end up with a whole set of decimals. All right. So all of this turns out to be I think you can simplify this, right? You can remove the bracket and so on. Let's remove the bracket and see what happens. You'll get 0.9 x squared plus 0.9 by 0.9 is what, right? 0.81, will that be right? Or 8.1? No, 8.1. What am I doing? Get 8.1. All right. Look here now. 2 by this. 2 by, you'll get what? 0.9.
1.8.
So you get minus 1.8x squared, okay? And 1.9 by 2 will give me what?
3.8.
3.8x, right? All of that over x squared plus 9 all square, right? Which will be 1.1 over x minus 1 square plus, and let me simplify all of this now. This minus that, oh gosh, you'll end up with some minus 0.9x squared, all right. This x term, oh, you know what? We made a mistake here. You see this minus sign? Times that will give you a minus here. Gosh, minus sign here. So you have minus 3.8x. And then the 8.1 at the end here. All over. Yeah. All right. Yeah. I mean, this is an exceptional one. Who would ask you something like this in a test? You never know, though. Yeah. So that's using, partial fractions there, right? And it can get a little harder than this too, but I'm gonna stick with the simple stuff. Don't kill yourself with too much. Because you can have, I think in the handout, right? I think I gave you, I think you can have something like this. Let's say x minus 1 over, let's say x squared plus x. No, take out this x. Okay, let me go with x squared plus 1 over x squared plus x plus 1. Let's say you get something like this. And you actually here have like what you call an improper fraction there, improper rational function. So you have to divide this by this. And then when you finish now, you get maybe 1 or something plus something over x squared plus x plus 1, right? You have another big story there. But I'm not going to get them that far. Right? That's for the more advanced student. All right, good. So yeah, can stop the recording now.